Hi, I'm Lia Talozzi. I'm a postdoc at University of Bordeaux, and I'm happy to be part of the Brain Parcellation educational course. And we are going to deal with latent dysphoneton prediction of long-term cognitive symptoms in stroke. In this project, we created a neuropsychological white matter atlas, NWMA. So we are focusing on the white matter, and we want to correlate specific areas in the white matter with neuropsychological scores. These scores were acquired for patients who had a stroke and were recorded after 1 year from the stroke onset. Here are reported the different acronyms of the scores that were 86 and colored by the different functional domains. Right motor function, visual spatial attention, sickness, left motor function, language, visual spatial memory, or verbal memory. A stroke happens when there is a cerebrovascular injuries in the brain. This injury will occur in different cerebral artery territories, the posterior, the middle, or the anterior one. And the stroke localization can be really diverse across the patients. Thanks to neuroimaging techniques, it's possible to visualize in vivo the stroke localization with a fast but poorly contrast using computer tomography, scans, or with more details using magnetic resonance imaging. Here, the stroke lesion is indicated by the red arrows, and you can appreciate how the different contrasts provide us different informations and images for stroke lesions. We analyzed different cohorts. The first acquired at the UCL London, dataset 1, that was the biggest, 1,343 stroke patients. Then other two dataset 2 and 3 acquired at Washington St. Louis. All the MRI scans were acquired within 1-2 weeks from the stroke onset, whereas the neuropsychological scores acquired for the cohorts in Washington for 1 year after the stroke onset, and 86 neuropsychological scores were acquired. So we deal with a problem that is the high variability that we can have according to the stroke pathology. So one of the goals of this project is to summarize this variability. I like to start with an example from Sir Francis Galton, who was a great statistician, one of the first. Indeed, the famous Carl Pearson wrote his biography in 1914, and he collected a lot of data about the human behavior. He was the first to administrate questionnaires to really collect the data, so a data meaning approach. And here in his publication in Nature 1907, he proposed a model to summarize the variability that he could find in many portraits of human faces. And you can see here how he really created a model to schematize this problem according to the variability. And it said, I have applied the above method to portraits, and as thus far, it is efficient in all of them. We wanted to find a model that will be efficient in all the stroke lesions that we can have. And in particular, we are going to use this word morphospace that derived for the morphometrics of Sir Francis Galton. And we're going to use it for stroke patients. In particular, we use dimensionality reduction techniques to make this problem easily understandable. Let's use a really simple example. So if you have emoticons of different faces, So they have different characteristics. They can have different sunglasses, different expressions. They can smile, they can cry, they can have their eyes in different shapes. And a dimensionality reduction algorithm use all this information, so the variability of the input data set, to derive a latent dimension or embedding dimensions, in this case 2, and characterize the input data with coordinates in this space. We used this connectome data. So we would like to analyze the variability of this connection in stroke patients. For doing so, we manually delineated the stroke lesions for the patients, and then we used the normative dataset acquired for the Human Connectome Project 7 Tesla to obtain whole brain tractography for 163 patients. Here, one of the connectome that we obtain, where you can see the white matter fibers passing through the stroke lesions. Here, the probability map, according to the healthy controls, the probability of these connections, and is plotted here in the MNI space where all these analyses were conducted. In particular, for the dimensionality embedded, we use the Uniform Manifold Approximation and Projection method, UMAP. UMAP is a new method that has really good performances. Indeed, if it's compared here to the TSNE method, Halo-Hebetter segregation of the data, or in terms of computational time, it is more stable across embedding dimensions, and it requires lowest time in comparison to the TSNE enlarged algorithms. This is the morphospace, this connectome distribution that we obtain. I highlighted 3 patients that were plotted in diverse area of the morphospace. We use the dataset 1, the largest, to obtain the UMAP transformation, and then we use this same framework to import new patients. Here, dataset 2 and dataset 3. You can see for the patient that I highlighted that the patient with a similar pattern of disconnection will be projected close by in the disconnectome space, so with closer coordinates. Otherwise, they will be projected far apart. Here, I also plotted the single tract disconnections. In particular, I reported 3 tracts: the cortical spinal tract, CST, the inferior frontooccipital fasciculus, HIFOF, the arcuate fasciculus, AF. You can see how they are clusterized in the morphospace. So when the highest probability according to one of these tracts occur, the patients are projected close by in the morphospace. This to underline the variability dimensionality reduction that we obtain with the morphospace. And as you can notice, there is a symmetry in this shape that is due to the laterality of the lesion localization in the patient. Then the neuropsychological scores that we are interested in. So they were 86, acquired at 1 year after the stroke onset. We can summarize them in the major functional domain. So motor, language, visuospatial ability, visuospatial memory, verbal memory, sickness, and pain. Here some illustrations of the tasks that were required to the patient. So hand grasping, pitching, 9-hole peg replacement, grip strength, shoulder and wrist extension. Or animal verbal fluency, the Boston naming test, or the Posner Visuospatial Ability test. Then we correlated the reported neuropsychological scores with the localization in the morphospace. And we obtained what we called a composite morphospace that merge these two informations. Here are reported 3 examples of neuropsychological scores for 3 domains: motor, language, and visuospatial. Focusing on motor, there is the left hand grasping from the ARA battery, and you can see has lower scores correspond to a deficit in this domain, and you can appreciate the clear segregation of the lowest scores in the morphospace. Whereas for language, the Boston naming test, and again, the lowest scores reported were associated to a poor performance in this domain. And you can see as for language, the distribution is more complex in the morphospace. Indeed, here I highlighted the clusters of correlations with R in module higher than 0.2, so with a medium effect size. And finally, for the Posner accuracy of disengage, you can see again as the lowest scores were projected in the morphospace. Here, the correlations reported were more bilateral. These are the scores that were recorded for the dataset 2 that served us as a training set for a multiple regression formula. First, we ran a principal component analysis to summarize with 3 components, so 3 scores, the neuropsychological variability in the embedding space. Then we used those scores as an input of the multiple regression formula to predict the one here affected neuropsychological scores. Then how going back to the neuroimaging space to create what we call the neuropsychological white matter atlas. We used the first data set because it was the biggest, and we split it in 2 alphas to assess the atlas reproducibility. And we ran pixel-wise correlations using FSL randomized. And we correlated the risk territories that I highlighted with the R in module major than 0.2 with the disconnectome location in the neuroimaging space. And here the results. For the left hand grasping, you can see the disconnectome patterns correlating with, in this case, they were on the right hemisphere with fibers going toward the parsopercularis, promotor cortex, superior temporal gyrus, or passing through the striatum. For the language score, we got correlations with the left fibers through the external capsule and toward the superior temporal gyrus and middle temporal gyrus. For the Posner's accuracy of disengage, more bilateral correlations passing through the corpus callosum, bilateral insula, bilateral striatum, right long segment of the arcuate fasciculus, or left thalamus. We run these for all the 86 neuropsychological scores, and we obtain a summary map. Here are the highest correlations across the scores, the acronyms of all the scores that now I didn't report it, but you can find it in our preprint that is currently under review. The clusterization according to the different functional domains. And then we also can create some maps. The first one in relation to the highest effect size obtained, so F square, And you can see that the highest effect size was on the left frontal connections, whereas the versatility mapping panel B reported the overlap of the neuropsychological finding in the white matter. And you can see as the highest number of overlap occurred for the right hemisphere. Finally, we really want to make this model transferable to an application, and we create a really usable web application. I leave you here the QR code so you can play a little bit with it. There is an example of one of the disconnectome you can upload and run the model online. In this application built in Python, the Django, you can run the model that I show you for the neuropsychological prediction. You have also a lot of descriptions about the neuropsychological scores. You can download the neuropsychological white matter atlas. Here, here's a little tutorial to going around the application. So the disconnected morphospace distribution, some information about the scores, so the acronyms that I show you in the summary map. That here you can see which battery was used, the references, and etc. Here you can upload the disconnectome of your patient, so for a personalized outcome, and you can run the analysis on wherever you want. So like it's not important which browser, or if in a computer or in a smartphone. And here it's plotted the outcome, so the UMAP coordinates and the score predicted. You can download this as a CSV file and use it for further analysis for your patient. So in conclusion, we summarize the variability of stroke disconnection using dimensionality reduction techniques, in particular UMAP. This allows us to run correlation analysis with the patient neuropsychological scores, obtaining a prediction formula that assesses long-term cognitive symptoms at 1 year, analyzing neuroimaging data within 1-2 weeks from the stroke onset. Then the neuropsychological atlas allow us to visualize onto the white matter the risk territories, obtaining the neuropsychological composite morphospace within the brain. Then the web application will really allow a broader validation of the model proposed, and really use it if you're curious about it and want to see your patient predicted outcome. Of course, I would like to thank you for the attention and all my collaborators that make this project possible.